So okay, basically the things that we are going to discuss in chapter 2 are basically the international system of units, the international system of units, then we have basically measurement of length, and we have the measurement of length, then we have the measurement of mass, then we have the measurement of mass, then we have the measurement of time, then we have basically the difference between accuracy and precision of instruments and errors in measurement. So it's something about accuracy and precision, of measurement instruments, Then we have basically the number of significant figures, then we have the dimensions of physical quantities, Then we have dimensional formulae and dimensional equations, and dimensional equations, Then we have the dimensional analysis and its application. So there's something called the dimensional analysis. And that's basically it. So these are the things that we are going to cover in this chapter. It's about 23 pages based on my experience on 23 pages that would take around probably 10-15 videos, meaning 10 to 15 basically hours to cover this chapter. So let's get started with the introduction. So the way that I'm going to do this chapter is that I'm going to basically read through the text, and I'm going to read through this text, and then wherever some explanation is required, I will explain, the best that I can, and then we will move through the chapter, and then we will go through the exercises. The exercises are very important, very, very essential, and and of course it's my first, basically. I mean, this is the first time that I'm actually working on physics. Of course, I have been working on physics before, but this is the first time that I'm working through these books. So, I mean, from time to time, I might actually change my approach and change the way that I approach the subject and things like that. But I mean, we will eventually find some way in each case to approach the subject, each part of the subject properly and efficiently. So as an introduction, we have measurement of any physical quantity involves comparison with a certain basic arbitrarily chosen internationally accepted reference standard called unit. So what a unit is basically, so for example, when you say for example 6 centimeters, this is some measurement that you make. You measure, for example, using a ruler, or using a meter stick or something like that. You measure some length, and you say that basically the length of this length is basically 6 centimeters. So this is some sort of measurement that you make. Now this measurement, if you basically pay attention to the process, basically if you pay attention to the process that you use in order to make the measurement, is that you have basically something called a meter stick or a ruler, essentially something like this, and there is basically on one side you have basically, for example, something like this, and so on and so forth. So for example, this part of this edge of the ruler is graduated, and so on and so forth, and for example this becomes 1, 2, 3, 4, 5, 6, 7, 8, for example 9, and so on and so forth. So that means that this line, that this edge over here is 0 centimeters. This length from here all the way up to here is 1 centimeter, and then basically this length would be 2 centimeters, this length would be 3 centimeters, and so on and so forth. And of course you know that 2 centimeters is 2 times, basically is twice 1 centimeter, 3 centimeters would be thrice 1 centimeter, and so on and so forth. Now if you pay attention to the sentence, so you basically, what you do is that you put this ruler against that. Suppose that this is the length that you want to basically measure. You don't know the measure of this length. You put your ruler, you fit your 0 to this point over here, and then along this edge you read the ruler, and then it tells you, for example, this is, I don't know, 4 centimeters or so, and then you say that this is 4 centimeters. So what that means is that you're actually comparing this length against some arbitrarily chosen standard, which is internationally accepted, and which is first of all, it is arbitrarily chosen, arbitrarily chosen and internationally accepted some arbitrarily chosen internationally accepted standard that, for example, we call a ruler. And this is basically based on some agreement between scientists that, for example, this is supposed to be, for example, 1 centimeter. Now, this part that says arbitrarily chosen means that, for example, on the first day that they chose this standard, they could have, for example, they could have taken this whole length as 1 centimeter. Or they could have taken, for example, half of it as 1 centimeter. They could have taken 1/3 of it as 1 centimeter, and so on and so forth. So it doesn't really, 3 centimeters is just simply, is just really only some agreement between people. It doesn't really mean anything it doesn't, it could have been chosen in any other way, really. But based on some reasons that have existed in the past, they have happened to have chosen this in this exact way that they have chosen. So then, based on this, you can say that the unit, and of course over here the unit of this measurement is this part, which is centimeter. So this is the unit. So what the unit is basically a certain arbitrarily chosen internationally accepted reference standard. Which is called basically this whole thing has been called a unit. Now, of course, you know that there are some units. There is a unit. There is a standard unit, for example, for length, for example, which happens to be, for example, in the current system that we use internationally is the meter. Or there is, for example, some standard unit, for example, for weight, which is, for example, the kilogram. There is some unit for example, for time that in the current system that we use, called the SI system, is the second, for example. So you cannot say that, for example, the unit of time, for example, the unit for time is not the hour, for example, or is not the minute. It happens to be the second, for example, and so on and so forth. So any sort of basically measurement that you make, whether it be basically whether it be in the case of measuring a length, or measuring the weight, or measuring the time, or measuring an electrical current, or measuring luminous intensity, and there is I think 7 of them over 7 of them really only. The basic units. Any sort of measurement that you make is only just some measurement. It's only a comparison against the base unit. For example, what that means is that, for example, we have defined, for example, 1 second. We know basically how long 1 second is. So now, based on that, since we know how long 1 second is, then any duration of time or any time period, we just simply compare it to the time length being basically 1 second, which is the unit here. And for example, suppose the time duration, the time length that we are trying to measure is, for example, the length of that time, for example, that time period is, for example, 5 times the length of basically 1 second. So then that becomes, for example, 5 seconds. Suppose that, for example, that time period is for example 10 times, for example, the length of 1 second. So that would be, for example, 10 seconds, and so on and so forth. So that's basically what measurement is. Okay. Okay, so the rest of this is, so it says that the result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. So for example, when you say for example 3 meters, some length is 3 meters, this measurement has 2 parts. There is a basically you have a number over here, and you have some unit over here. And so both of them have to be together so that basically, so that the result of the measurement is actually meaningful. You cannot, for example, if you say 3, it doesn't mean anything. It could be 3 apples, it could be 3 hours, it could be 3 meters, it could be 3 seconds, it could be 3 people, it could be 3 anything. So 3 in and of itself doesn't mean anything. Moreover, when you say meter, if you say meter basically without a number, meter is just simply the unit for the standard unit for length, and it doesn't really mean anything without a number. But then if you put these two together and express this as, for example, 3 meters, then 3 meters is basically the result of a measurement that you measure, for example, some length, and that length, for example, becomes 3 meters, meaning that if you have a meter stick of length, for example, let's say that this is your meter stick of length, for example, 1 meter, or 1 meter, then the length that you have measured, the length of that, well, the length of that length has been basically 3 times the length of your meter stick, or your basically your standard, and based on that you express that as 3 meters. That's basically what that means. So it says that although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities, since they are interrelated with one another. What that means is that, for example, you could have, for example, what basically a physical quantity means. What a physical quantity means. Now, I cannot give you a good definition right now, but a physical quantity is, for example, length. It could be length. It could be, for example, time. It could be, for example, speed. It could be, for example, pressure. It could be, for example, I don't know, energy, for example, or the amount of energy, or something like that, or work, for example, or something like that, or force, for example. So for example, you know that for length we use, for example, let's assume that for length we use the standard is the meter. For time we use the second. For speed, there is no individual unit for speed. Since you know that basically speed is the rate of change of position of an object, then the rate of change of position means that is the ratio of basically position to, for example, position to time, for example. Because you're measuring the rate of change of something, you need to have time in the denominator. You need to have basically distance or position in the numerator. And so over here you have meter, and over here you have second, so the unit for speed becomes meter per second. That means that no matter how many basically physical quantities you might have, they are all expressed in terms of the basic units. And the basic units, there is only, I suppose 7 of them or 6 of them or something like that. And then all the other physical quantities, and there is excuse me, and there is a lot of them in physics. All of those physical quantities are expressed in terms of those basic quantities. For example, pressure is, for example, I don't know, there is a unit for it is I don't really know or remember the unit for pressure, but for example, let's say the unit for example, there is something in physics we call rho. It is denoted by rho, which is basically called the density. That is density. So for example, density is basically the ratio of how much basically space something takes, how much space some object takes up by the how much space something takes up by the mass of the object. By the mass of the object. So then basically, for example, suppose that something takes a whole lot of space and it has not much mass. That means that then that material or that object or whatever that is not very dense. It is really not very dense, like for example, like gases. On the other hand, suppose that some material takes too little space, but basically taking up too little space, it has a large mass, relatively large mass. Then in that case, the density of that material is very high. Now, space is basically measured in cubic meter. Meter times meter times meter, meaning that you have, for example, let's say you have a cube over here, and this cube is basically something like this. Now this is basically how you measure space or measure basically volume in physics, basically. So there is basically some length over here, some length over here, some length over here. This is in meter, this is in meter, and this is in meter. You multiply this by this by this, and then you will get some number, a cubic meters, for example. And then the mass of the object is of course measured in kilogram. So then the density, the unit for density would be, I suppose, cubic meter per kilogram or kilogram per cubic meter, something like that. We will get to that, of course. But now basically the point of this discussion is that basically all of those basic units that we have, which is there is only like 6 or 7 of them, then in terms of those basic units, all the other physical quantities in physics are basically expressed. So So the next thing that we have is that the unit for the fundamental or base quantities are called fundamental or base units. So the unit for fundamental or base quantities are called fundamental or base units. And that would be, for example, the unit for length, the unit for mass, the unit for time, the unit for example, basically luminous intensity, electric current, and there is only a couple of them. There is the unit for heat and something like that. There is only a couple of them. So these are the fundamental units. And then the units of all other physical quantities can be expressed as combinations of these base units. Such units obtained for the derived quantities are called derived units. So from this you will get the derived units. And I gave already an example. So for example, as a part of these fundamental or base units, you have, for example, the unit for distance. The unit for distance is in meters. The unit for distance is length or meter, basically length or distance. The unit for length is in meters, and and the unit for time is the second. Now, so these are basically two examples of the fundamental or base units. Now the derived units, for example, as an example for the derived units, you have, for example, speed. So speed, by definition, is the rate of change of position. Is the rate of change of position. What that means is that suppose that you have a car over here on a let's say on a straight road, for example. You have a car over here, it starts at this point, and after some time, for example, at T1 it's over here, at T2 it basically reaches this point over here. Suppose that I call this point x1, and this point I call the length of this point, I call it x2, with reference to some coordinate system, for example. Now the distance between the distance between x1 and x2, it has taken the car some time from T1 to T1 to T2 to basically cover that distance. Now, the faster that the car basically covers this distance from x1 to x2, meaning that the less time that it takes the car to cover that distance, the higher is the rate of change of position. So the position first is over here, and then the second position is over here. So the faster or the higher the rate of change of position, then basically we technically say that the speed of the car was basically higher. The more time that it takes the car to get from point x1 to point x2, then the lower is going to be the speed, meaning that suppose that, for example, it takes, let's say that this distance is 2 kilometers. And for example, let's say that it takes the car, for example, let's say that it takes the car, for example, 1 hour to cover that distance. So then your speed is basically the ratio of these 2 kilometers per hour, or you can say 2 kilometers per hour. That is the rate of change of position. Now, the less time that it takes that it takes the car to cover the same distance, the higher is the rate of change of position, meaning that v, for example, let's say that your v is 2 kilometers per half an hour. Half an hour. So that's going to be 2 divided by 1/2, which is 2 times 2, which is equal to 4 kilometers per hour, right? So you see that over here your speed was higher because the time basically was, that's basically the time that it took the car to get from this point to this point was actually lower. So speed again is the rate of change of position, and when you use the word rate, that means that time is always there. The time is always there, otherwise rate could not be basically measured without, if you didn't have the concept of time, then rate of course could not be measured. Rate always means time is present there. So when I say the rate of change of position, that means how fast the position is being changed, and how fast means again time is there. Now, long story short, basically these basically derived units, and as an example of that, for example, you could say speed is basically then expressed in terms of these fundamental or base units, which is, for example, the unit for speed is meters per second, for example, in the SI system, and we will talk about what the SI system is. Now suppose that you have all of these fundamental or base units, for example, distance, time, electrical current, and there is only a few of them, just probably only 6 or 7 of them, and there is a whole bunch of these derived units derived from these base units. So then if you put all of these together and make a system out of them, with which you could basically measure probably and hopefully everything in physics, or measure every basically physical quantity, then that system would be called a system of units. A system of units. Now, basically in the past there has been many sorts of units, basically many sorts of units around, and there has actually been many, at least a couple of very tragic disasters happening in science and technology and in space, and I suppose I read somewhere something happened even in space to some satellite or to some spaceship or something like I don't remember what that was. And the problem with that was that basically the different countries around the world, for example, the different countries around the world, they used different systems of units. For example, there was the CGS system of unit, there was a CGS system of unit, there was the FPS system of unit, there was the MKS system of units, and so on and so forth. There were, of course, many other systems of units. So in this system, for example, this is the centimeter. This is the centimeter, basically gram second. Gram and second. So for example, in this system, in the CGS system, the unit for length is centimeter, the unit for mass is gram, the unit for time is second. In this system, this is foot pound second. Okay, this is foot pound second. This is foot pound second. So this is again the unit for length, the unit for mass, the unit for time. In this system you have MKS, meter kilogram second. This is meter kilogram, for example, second. So again, this is the unit for length, this is the unit for mass, this is the unit for time. So now you can imagine that basically different countries in the world, and basically the main ones were mainly used in the UK. Basically UK was one of the countries that seems to have had their own system of units. It's called the British system. And then there was also the US, that they had their own system, and then other countries in the world were basically in one way or another using either the system basically used in the US or in the UK. So that's basically what was going on in the world before the SI system basically was agreed upon by scientists around the world in France around, probably I think around 100 years ago or so. Now, of course, you know that converting between different systems is not as an easy job, and you tend to make mistakes all the time. And for example, if I say something in terms of foot and your system your system measures length, for example, in terms of centimeter, then you have to convert everything, and then it's not always easy to convert because numbers don't always fit together properly. You get basically decimal points and things like that. You won't get whole numbers, and such problems also exist all the time. And moreover when you convert numbers, you tend to make mistakes. So as a result of such problems, for example, there was this incident where some spacecraft or spaceship or something like that, I think, crashed or something happened to that, and that was many thousands of dollars basically went to waste because of that simple mistake that, for example, some scientist made for reporting, for example, some value measured either on Earth or on the spaceship or something like that. And there were some such incidents happening around the world, and then scientists basically decided that there had to be there had to be some unit, some basically some standard system upon which everybody, everybody had to agree upon just one single system, and then all of this confusion and all of this problem of conversion and so on and so forth could be taken care of. And so they made the SI system. So now it says that over here, it says that the system of units which is at present internationally accepted for measurement is the SI system. The SI with standard scheme for symbols, units and abbreviations was developed and recommended by General Conference on Weights and Measures in 1971 for international usage in scientific, technical, industrial, and commercial work. Because SI units were used the decimal system, conversions within the system are quite simple and convenient. Decimal system meaning that it uses a system of basically I suppose base 10, or because everything is based on converting between 10 raised to the power 0, 10 raised to the power 1, 10 raised to the power 2, and so on and so forth. So we shall follow the SI units in this book. Okay. Now there are some definitions here. We will go through these definitions and to see what they are, and we will continue with this chapter. Okay, so the next thing that we have here is basically in SI, or in the SI system, there are 7 base units. So the 7 base units, as I mentioned, I wasn't sure really about the number of them, but 367. So there are these 7 base units which are given in a table in a book. So the base quantity could be length, it could be mass, it could be time, it could be, for example, electric current, it could be thermodynamic temperature, dynamic temperature, it should be written like this: temperature, and it could be amount of substance, amount of substance, it could be luminous intensity, So we have these 1, 2, basically 1, 2, 3, 4, 5, 6, and 7 base quantities. So the name for basically there is a name. Let me draw a table over here so we know what we are doing. So there is always, for the unit, there is a name for the unit, and there is the symbol for the unit. So for example, in this case, in the case of, for example, length, the name for the unit is, for example, meter, the meter. In American English it's written like this. In British English the meter is written M-E-T-R-E. But anyway, it's the meter. In different languages it's written in different, there are different words for it, but the unit is the same basically. Now the name for the basically for the unit for the mass is the kilogram. The name for the unit for the time is the second, is basic, the name is second. For electric current is ampere. For thermodynamic temperature is Kelvin. For amount of substance is mole. For luminous intensity is candela. Now there is something else called the symbol for this unit. Now the symbol for the meter is lowercase m. The symbol for kilogram is lowercase k, lowercase g. The symbol for time is lowercase s. The symbol for electric current, the symbol for the unit for the electric current is uppercase A, amps or ampere. The symbol for thermodynamic temperature is uppercase K. The symbol for basically amount of substance or mole is MOL. And the unit for the luminous intensity, or the symbol for that, is CD. Now this meter basically actually, well, of course it does mean something. And for example, what the meter means, for example, when you say 1 meter, meaning that, for example, the meter stick that you have, for example, with which you measure length. That length is basically based on some definition and some agreement between people. And so, for example, the meter is the length of the path traveled by light in vacuum during the time interval of 1 divided by 299,792,458 of a second. And this definition goes back to 1983. So that's, for example, in case of the meter, it's the length traveled by light in vacuum. The length traveled by light in vacuum during a time interval of interval of 1 divided by 299,792,458 of a second. So that means that basically what that means is that the path traveled by light in vacuum, the path traveled by light in vacuum is 1 meter, whatever that path is, we call it 1 meter, and that happens in 1 divided by basically 299,792,458 792,458 of a second. Okay, of a second. So what that means is that so if you want to know, for example, what is the distance that light travels in, for example, 1 second, then you can use this what do you call it, relationship. There is a name for this relationship, and you can cross multiply. You can write x times, for example, this quantity is equal to 1 times this quantity, and then x would be, this is in 1 second and this is in meters. Okay, because this is in meters, this is in second, then this becomes in this will be in meters, and this will be in seconds as well, because this is a proportion basically, or a ratio basically. So then x times, for example, that means that x divided by 299, I'm sorry, x divided by 299, 792, 458 is equal to 1 times, well, it's just 1. So that means that x is equal to 299, 792, I suppose. Is that right? Yes. 792, 458, and that is in meters. That means that basically the length that light travels in 1 second in vacuum would be 299,792,458 meters. And if you, for example, want to express that in kilometers, that would be 299,000, for example, kilometers, and so on and so forth. So that is basically, that's close to 300 million meters, or basically 300,000 kilometers in a second. Very close to 300,000 kilometers in a second. So, for example, that is one definition for the meter. For the mass, there is a definition, and what that is, and you need to understand each one of these, because, for example, when you say 1 meter, of course, everybody, for example, today understands what one meter is. For example, we all know we have all seen a meter stick, but then you need to know based on what, I mean, this meter stick is basically compared to something, is a comparison to something, or to some definition, or to some basically natural phenomenon, or something like that. For example, this the agreement that we have for meter happens to be based on some natural phenomenon. This, for example, based on the speed of light, and so on and so forth. For example, in vacuum, something like that. Or when you say, for example, 1 kilogram, then you need to understand what that means. When you say 1 second, you need to know what that means. When you say 1 amp or 1 ampere, you need to know what that means. Oftentimes what happens is that, for example, students, for example, they actually, basically, they are given a problem, they actually solve the problem, and they actually even get the right answer. For example, the answer becomes, for example, 2.5 amps. there is some electric current going through some circuit, some wire, for example, something like that. The electric current I, for example, becomes 2.5 amps. Now the answer is correct, but usually, I mean, it happens so often that the student or the person that basically solves the problem and gets the right answer doesn't know what this number actually means or what this number actually represents. So, and of course it doesn't really make any sense to do such a thing, meaning that you take your time, you solve a problem, you do the calculation and everything, and you get a number, and then you don't even know what you could do with this number. For example, suppose you calculated in a problem, you calculated, for example, some mass, for example, and this mass came out to be, for example, 2.5 kilogram. Now, 2.5 kilogram, you need to understand what this 2.5 kilogram represents. For example, if I gave you, for example, some mass, and then if I told you, for example, out of this mass, give me, for example, 2.5 kilogram, you need to be able to do that. You need to understand it. Otherwise, the whole thing doesn't really make logical sense. So now the next one, for example, the mass and the unit for that is the kilogram. The kilogram is equal to the mass of the international prototype of the kilogram, a platinum iridium alloy cylinder kept at International Bureau of Weights and Measures at some place near Paris, which goes back to and the definition goes back to 1889. So, for example, this basically refers to some cylinder made of platinum iridium alloys, which is kept in Paris, and then basically they have made all of these replicas, and based on that, and then those replicas are kind of calibrated against that basically against that standard, and then it will be distributed all around the world, and then everybody knows basically what 1 kilogram is. Or basically the unit for time is which is the second. It says that the second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. And the definition goes back to 1967. Now, unfortunately, for example, for now, we cannot really understand definition because there are some words in this definition that we do not understand right now. So we need to just leave it for now, and then when we know more about the atoms and the radiation and the subatomic particles and things like that, then we will be able to understand this. So, and there is a couple more here.